Morning. No, I was saying the same as that one.
Sorry?
No, I can say the same as asked to say the same.
The end result will be great if you just then say, and this is how no, the application is actually quite important. If you've got a long there can be, especially over alien amplifiers, which then seems to be a matter of interest. You could end up with amplifier gain that is entirely opposite spectrum. What you can do is some carriers and really PS gain and close the link with the whole sequence.
The spectrum is completely interleaving thing means that you kind of spread quite widely across the spectrum just for a single one. So all I see, so the ones which are at the edge of the spectrum, so the ones to center, which has got more gain.
I mean, we've got dynamic spectrum equalizers and stuff like that, but you know, some of these limits, if you're clawing back that 2 dB of margin, service providers want more, then it can be actually quite useful to switch.
Just in general, you know about the open process that we support open engineering. It was briefly mentioned. Essentially, we've got 2 million fundamental UCs kind of ring fence. So we've but no, we are one of the things there was software configurable correction. I'm thinking refining that software configurable. So that would then go about 5 hours. You can do with software
some level of capability of iteration. Some level of software.
Right, so
So good morning, everybody.
Morning.
And welcome to the second day of our day1 workshop. We also have a very busy schedule today, so we're going to start straight away. First presentation is time-sensitive transport by Henrik Wessing from DTU.
Thanks a lot, Alberto. And what I'm going to do is I'll be reporting on some ongoing work. It's a subtask within day1. And I am representing Technical University of Denmark, DTU, and we have been included in this, I guess, because we seem to have some kind of broad knowledge about mainly all the layers from 0 to 7. If you were at the Nordnet conference, there'll be quite some similarities with that speech we had there. And we can also discuss how much new you'll have in this. It's really not rocket science, but it's a way of structuring things. The delay components from the different technologies in a nice way. That's what we are striving to do. It is a collaboration between Forchang, Janet, Nordnet, Uninet, and DTU. So, what's the motivation for doing this? And clearly, the key question is, when would we like to have circuit-based path, or when would we like to have packet-based solutions, or when can we survive with the packet-based solution, seen from a delay perspective? So, what we are doing is that we will, it took us some time to really understand how can we try to look at this in a nice way. So we took a bottom-up approach and say, okay, we try to see what are the delay components in the lowest layer. What are the delay components in the layer 1, in layer 2, 3, and so on. Probably stopping there. And we know very well that there will be orders of magnitude difference between those different layers. But still, we found that it could be relevant to understand the delay components in the different layers anyway. So, we'll go through some technologies and layering. And there's some delay verification. We can do that using dedicated test equipment or some OEM, depending on the purpose. And the layers I'll discuss will be the physical layer. I'll take the O10 layer, MPLS, TP, and PPT. I'm not going to any religious discussion about that. And I didn't even mention TMPLS, not to go there at all. And there's some measurements and conclusions, and also the continued work, because as I mentioned, this is an ongoing task, and I would pretty much, and I very much like also to have your feedback and say, there you said something really bullshit. Please correct me then. Low delay. It is a key property, and we had this discussion from Jan also about synchronizing atomic clock. Then we had some delays, jitter requirements in the picosecond scale. That is really tough. But if we go take a slightly different thing, then there could be some kind of online music production. There's this project called Lola, guys behind that, where we have requiring low latency audio and video conferencing, delays less than 35 to 40 millisecond for the network part, and jitter less than 3 milliseconds. And again, this is characterized by many small packets. We'll see how that has an impact later. Then there could be other things like telemedical surgery. It is quite convenient that when you're making some operations, surgery there, that you actually have some, if you have a second opinion, that you agree, and this is the heart and not the kidney. It could have some fatal consequences. And in this case, we also need gigabit per second bandwidth, because we cannot tolerate compression, because that also inherently gives some delay. Another interesting thing could be that the NVENs work with as interconnection part of data centers. I'm not sure that is happening right now. Again, correct me. But that also definitely sets some requirements to delay. And then we have this, been a lot of fuss about this discussion, the banking, the stock exchange thing, where they use some kind of algorithms and just by winning a few milliseconds, they claim to be able to earn millions. I don't see that this is a business for the NVENs to be in that area, but just to indicate that this is also a driver for low delays. They are putting cables where they are with the shortest distance from Europe to North America. Unfortunately, this is also exactly the rate that all the ships are sailing. That could have some impact there. And according to the Telegraph, it says that 1 millisecond advantage could be worth up to $100 million a year for one of the larger hedge funds. There might also be some political things about this, but it's just to indicate that there's a driver in this as well. And there are more and more services coming up, indicated a few of them in these color graphs. The variety of service, there are different requirements, and we need to support them all with their needed requirements, with different error tolerance and delay tolerance. And here it's also with the bandwidth in top and low bandwidth in the bottom part of the boxes. These will also seen also in the INREN community. So we are investigating a lot of technologies, and there's also a lot of terminology that's actually different wherever you are in the INREN community or in the more traditional telecom business. When we talk about campus networks, metro networks, that part. Traditionally, it is still layer 3 IP, layer 2, some kind of switching, depending on what it's used for. But often also pure IP, maybe with some kind of quality of service mechanism for those clients where we are emulating circuits for voice application, for instance. Typical technologies in the campus part will be IP, PPT, MPLS, GMPLS, MPLS TP. Probably not that much OTN, as it's more for the core. It's OTN and then the dying SDH Sonnet. Well, I still like that, but good old SDH. Anyway, but that's still a lot of that for the core network. And and now we'll come in to see what are the requirements for and how can we look into these different layers. Measuring delay, we can do that 2 different ways. We can use dedicated test equipment. However, that's of course disruptive. So if we want to measure delay and do that while the things are in service, we need to use and understand the OAM, and there was talked a lot about OAM yesterday, so I'm definitely not going into details about that. Just to indicate that there are ways of monitoring from different parts, both from all the subscribers. There could be some for different parts of the network, and things that we can use this OAM for is to get the delay things, get the information about the loss, get information about availability of the service in different parts of the network, and that is of course very important. And I've stolen this figure here from the Metro Ethernet forum, and you can see how the different maintenance entities, they stretches different parts of the network, and having this up orientation and down orientation depending on who it serves, for who it has its purpose, so to speak. And what can we, as I mentioned, get from this? It's specified from the Metro Ethernet forum, and it more or less applies. It's more or less the same concept, whether it's for the Ethernet or whether it's for the OTN. As with these different OAM, there's some difference, of course, but basically we get some kind of frame delay in some kind of bins, histograms. We can get some kind of frame loss ratio based on some counters, and the availability. And what we can measure is one-way frame delay using some kind of timestamp sequence number. We can use real data, or it can be added as synthetic frames. So of course this has some kind of disruptive nature, and that will, if you go one way, we require some synchronous clock, either done by IEEE 1588 GPS or whatever kind of clock synchronization you want, or estimated from a two-way communication. and some of the communication messages that are used, and they have different term again depending on the real technology. Delay measurement messages, delay measurement responses. So in that way you can get some kind of performance measurements for single-ended loss, performance measurement for dual-ended delay, using the service frames, and also for counting the lost frames. Such delays are usually stored in some kind of 15 minutes intervals. What we did however was using dedicated test equipment, and we used 1 gigabit links, and of course that has a huge impact for when we come to the PBT. But we used some Ixia solution, and the main advantage is that we can make a fully RFC 2544 compliant test, measuring the loss, signal power delay, jitter, with different packet sizes, which has a huge impact. As we will see, we can go from all the way from services to the fiber. In this case, we kept it to the Ethernet frames, and of course we used some Agilent equipment. We could also use Spirent, Sina, whatever, and in some of the, actually in one of the other tests we are using Spirent testers, so this is not the full picture. That's from some later measurements that used Spirent. So this is not to be some kind of commercial for advertisement for Ixia, not at all. Oh, but anyway, going to the physical layer, what are the delay contributions from there? Of course, it is a propagation in the fiber. That is the main delay component there. Of course, depending on the length. And a rule of thumb, 1 kilometer, approximately 5 microsecond. Now there might be some of you physical guys that say, if you're making this strange kind of fiber, then we might speed up things a little bit, and so on. And if we cool it down to and only run at the North Pole, it might also be different. But most of the circuits we have is not at the North Pole, so maybe this rule of thumb is still quite valid. Then dispersion compensating fibers, if we need to use that, we also need to find out that it might increase the delay with 10 to 20% extra length that we need to add. There are some other ways of doing the dispersion compensation where you don't have to do that. I'm not into details about those physical things, and so bear in mind that also the dispersion compensation will actually add to the delay, and there will be some delay in the modulation format depending on the technology, and also depending on whether it's, for instance, processed digitally. The modulation, it will take some delay again, whether it's QPSK, QAM, or FDMA. And as some kind of rule of thumb as well, again, the transponder in each transponder MUX ponder usually adds the delay about 5 to 10 microseconds. So each MUX ponder equals 1 to 2 kilometers of fiber. Just to put it in some kind. It's good to have this as a reference to say, okay, we have 1 microsecond. What does it mean actually? So again, for medium to long range application, propagation delay is the main significant layer 0 delay contribution. This is definitely not surprising at all. Then for optical transport network, OTN, what are the delay contributions there? Well, what we have is that we are mapping things from the higher layer to the layer 1. That adds some delay. We are doing forward error correction. That's probably the main thing. Yes?
You mentioned the transponders. The new technology 100G, when you have a more complicated receiver side, current receiver with DSP, you know,
I'm not exactly sure how much delay it adds having this often digital processing of the that depends basically how many clock cycles do we need, and how long does it take to have a stable QAM or OFDMA diagram. Anybody can give us some hints of how long will that take?
So the coherent side of it adds 7 or 8 bits of delay. You can't buffer at that speed. You know, we operate on that sort of level, so it's kind of 7 or 8 bits of delay from the coherent side, i.e. nothing. The FEC carries, because it's block phase FEC, but depending on what FEC you use, you can get some very different delay measurements. And back to the conversation yesterday, and that's whether you use nothing or G79 or one of the many vendor proprietary FECs, they all have lots of different trade-offs. And that's a much bigger effect at layer 0.
But you'll probably end up with a net benefit of being coherent because you're losing all the dispersion compensating fiber.
That's exactly so. There you have a trade-off there, and if you say it's only 7 to 8 bits, 7 to 8 bits or clock cycles, then it's definitely less than what you would add from the dispersion compensating fiber. That's a good figure I got from you there. I need to write that down. Yeah, it's actually. It would actually be nice. So I got to need to grab all you vendors afterwards to get some numbers, which we are of course also going to measure. True. But we don't have for the OTN measurements. I will describe that later. We don't have equipment from all of you. We have some from Alcatel-Lucent, and that is the one we will mainly be using for the test purposes. But anyway, if you have some OTN equipment, you don't know what you have to do with it, I will give you my business card afterwards, and then you just mail it to me. Oh, well. But the forward arrow correction, we believe that this is the main thing, and that's again very proprietary and vendor specific. Where did I come from? Yeah, OTN, it is basically a technology to replace SDH. It is cheaper, more flexible, and better suited for Ethernet transport, especially with the ODU2E, and also ODU4 is quite useful for 100 gig Ethernet as well. And it also includes, as I mentioned, this kind of time stamping, delay measurement messages, delay measurement replies, and that's also to be used in the evaluation. And for the vendor support thing, is all the vendors they are acknowledging OTN as from what I can see. I don't think anybody will believe that SDH will be the. There's a future in that, even though it has done its deal, sure. The measurements we actually will do with the OTN, we haven't. It's more or less been set up now, the setup, but it had taken some time. It's using some Alcatel switches. It's those ALU 1830 in a triangular setup, with one in Copenhagen, another in Copenhagen, and one in Hamburg. We also had an idea of having one in Copenhagen and one in Oslo and one in Hamburg, but that somehow reason did not work out. And basically, we would like to go through this in triangles, having simply a ODU 0, and then raise around as many times in this triangle as possible, so we can extrapolate the delay coming from the mapping, the delay coming from the FECs, and also taking the fiber propagation delay again out of the equation. So trying to quantify what are the delay components from the OTN side. Not just what they are claiming in their data sheet, but here we'll make some real tests about that. But of course, I would also like to have the data sheets on what you expect that will be the delay for these different parts. And we expect this to be in microsecond range for these mapping and processing. I don't know whether you can confirm that from the vendor side. That delay will be in microsecond. If you say nanosecond, then that's interesting. But so making these loops in the triangle, that's how the way to quantify delay from the mapping, from the processing, and the fake addition and fake calculations. Then going up to layer 2, and of course here we begin to add the delay, especially when there are no free available bandwidth all the time. We have these MPLS, TP, and PPT. I'm not, as I mentioned, not going into any kind of religious war about that. There are 2 flavors, MPLS TP and TMPLS, depending on. And we heard yesterday that as soon as it became MPLS TP, everybody was happy and nobody wanted it. But it does not require a signaling protocol, taken out from the MPLS way, as it was usually. And legacy Ethernet can be transmitted using pseudo wires transported over MPLS LSPs. There are some delay contribution from the label processing, from the store and forward. It can be done at wire speed, or as they are seen, no CRC check, as we have the PPT. And again, depending on the switch design, lower priority packets may delay if they are in the switch fabric. Of course, if they're not there, then we can hold them back. I'll come back to another way of doing this in a while. PPT, it's Ethernet for the transport purposes. We've seen that a lot yesterday as well. Going from the legacy Ethernet into the VLAN, into the Q-in-Q, and that was not enough, so we invented Mac and Mac. That was not me, it was a lot of other clever people. And there was the delay contribution from the MAC table lookup, store and forward due to the CRC. We need to check the frame check sequence before we actually know whether we should drop the packet or forward it. So it is also, that means that it will be dependent on the packet length, as we will see. Lower priority packets, they may delay again if they are in the process. Until yesterday, I also had a statement on the slide saying who was back in the different solutions. I took that away because I was claiming that Sienna was mainly for PPT, but they are just as much for MPLS TP, so I could get into deep trouble if I kept such firm statements. But they have their support from different vendors. For the PPT, we did some tests going through up to, for a specific vendor, 5 PPT switches to see what the delay are from that. I can tell it's from some TPAC switches, kind of virtual switches, however. So it's a very simple TCP solution, and we will in the coming days work this together with the OTN, so we also will have the PPT, map the PPT into the OTN, doing some triangular tests, coming back through a PPT, and then measure delay again, trying again to quantify and qualify each delay component. And some first PPT measurements. For some reason, my jumbo frame graph, it's some kind of vanished. But the delay in microsecond is depending on the number of PPT. But what I show here is the delay in the microsecond depending on the number of PPT switches. And for a jumbo frame of 9,000 bytes, we can see a delay of approximately 80 microsecond for a 1 gig connection. So that definitely adds up. And if you have these 5 nodes, it's 400 microseconds. And then we can calculate how much that equals. And that means about 16 kilometers of transmission it takes to process each jumbo frame. If it's for 1 gig. If it's for 10 gig, it's, as a rule of thumb, we can more or less divide by 10. But we will probably see a lot of 1 gig in the loop. So that definitely adds some delay, which is inherent because of this check sequence we need to do. So it's that's actually quite important. And for this specific vendor, we also measured when the delay when we increased the load, and there was some tendency that when we got very close to 100%, we also had an increase in delay about 1% or in that range. Nothing serious, but that's probably what we can expect there. Any questions?
No. So we have 2-3 minutes.
3 minutes. Oh. Then I added this slide also from the Trench Packet Fusion H1 devices that we also been looking into. Some work done by it's mainly from Uninet, and it's some device that allows both circuit switch and packet switch in one device. And here we have some kind of it can then serve two kind of traffic types: guaranteed traffic, GST, and statistical multiplex traffic. And what this specific device this device does is that when a normal device would say, okay, we have some high priority and then we have some low priority, and whenever there are empty space, then we can add in this statistical multiplex, but that might not necessarily fit in the gap before we have new guaranteed traffic that we should serve. So the guaranteed traffic will be delayed a bit, as I also mentioned for the two types previously. So what this device does is that because it knows something about the GST traffic, because that's come from for instance, 1 gig link that is multiplied into 10 gigs, so it knows about it, and therefore it will only insert amount of statistical multiplex data if the gap between the GST traffic is large enough, meaning that we will not add jitter to the guaranteed traffic. And basically we saw that also for it's a bit a total propagation delay of 280 microseconds for some large fiber spans between 3 switches. We have a switching delay about 45 microseconds. That seems quite compatible with what we saw previously, and there are basically no delay variation for the GST traffic.
Just to add that it does in this way in order to maintain the packet delay variation for the GST traffic.
Yeah.
So the packet delay variation will remain the same.
It was at least in the nanosecond scale, so no jitter there. And that leads me to the conclusion, and then I can see Alberto is relaxing a bit. That this is a subtask within the GN3, and we try to quantify different delay contributions, put them into some kind of structure. It's not heavy research, just things that need to be done and tested and verified. There's some look into applications, this online entertainment, atomic watches that need to be synchronized, telemedical applications, banking, even though that's not an in-range task. And we also, first of all, it took us some while to have a common understanding of how to do this. We had persons in this group just that some of them were transport layer persons, some more on the IP plus layer, and when we decided to take a bottom-up approach and trying to verify delay contribution from different layers, and we are continuing doing that, and we'll hopefully have the OTN up and running next week or next week after, and do the same measurement we did with the PPT also in an MPLS TP setup, so we get the full picture, and this will be made in a small report. Okay, that's it.
Okay. Any questions for Henrik?
One question. Do you expect the same delays with MPLS-TP?
I would expect shorter delay. I don't see that it's necessarily that'll be very depending on the vendors, of course. But I don't see there's a need to wait until we have verified the packet before transmitting it. But that depends on whether you're implementing any checks that need to be done before whether you're deciding to drop the packet or not. If not, then you can actually send the packet before you have received the full packet. Sorry?
For TP, you still need to do your CRC.
Yeah, because you're still carrying over an Ethernet physical port. So it's Ethernet over or something over MPLS TP over Ethernet.
The question
so
is,
it's still a 22-byte header.
in that case, it will be the same.
I think it will be the same, because the processing that's going to be added by looking at a label or at a Mac and Mac label is going to be the same. I think what you're saying is the store and the CRC calculation eats the most of the delay, so I think it's going to be pretty much the
If
same.
it's on top of an Ethernet, it will of course be
Yeah.
the same. I don't know whether it could be on other kind of ports, and in that case it might be different. But we definitely will verify this and see. But in that case, it's for sure it will be the same. And then that cannot be the one that comes with the magic answer in this MPLS TP PPT discussion.
Okay, thank you, Henry.
You're welcome.
So next presentation about OpenFlow.
I don't know.
I don't know if the exact title is
Vendors review on OpenFlow implementation.
okay, and it's by Johan Tools from Nordnet and DTU. Automatically you click here, nothing happens. Okay, so you're the first one having trouble. You know, we put it in my computer.
Okay, I send it to your mail.
Yeah. You must have a strange setup in because usually it works.
It's just I'm not so familiar with this.
No, but it should be straightforward.
Send. Yeah.
So sorry, some problems with
The PPT. Yeah.
yes.
So, hello, my name is Johan Turus. I am a PhD student in Nordnet, and I've been involved in JRA1, where in task 1, subtask 1, we are doing an OpenFlow technology investigation. And my part of work here was to do a vendors review for OpenFlow implementation for all different vendors that are looking into SDN. The outline for the presentation, it starts first with a few words on SDN and trying to place OpenFlow in the SDN picture. Then I will take in almost a random order the vendors and say who's doing what with OpenFlow, and then the collaboration between them, the ONF consortium who is driving OpenFlow, and some conclusions. So there are many ways of approaching and explaining SDN, so I will try to refer to the idea of centralizing the control plane against distributed control plane. So in today's networks, the nodes that the vendors provide, they have
most cases specialized or proprietary hardware, specialized control plane on top of that, and dedicated features over. So deploying these nodes in a network, we have the intelligence or the control plane distributed, and this gives a couple of drawbacks that SDN will come to counteract, and these are the difficulties in flexibility. So if a customer is asking for a specific feature, then it's very hard and it takes long time, or the customer needs to be a very big one in order to drive the vendor into implementing those changes. It's also hard to assign network resources in a similar manner with cloud computing, so in direct relation to the requests. Then SDN comes with the idea of having very simple nodes, if possible without, or not necessarily, but they can be without any logic on top of them, and implies three main components. The first one is a so-called southbound API, which has the role of taking the intelligence from an upper layer into the nodes and controlling them. The purpose of the idea for this is to be open, so it doesn't matter what boxes are on top, they can be controlled from a centralized point. And one option for this southbound API is OpenFlow, but it's not the only one. On top of this, it's the operating system, a centralized one, which can be any operating system, proprietary or open source. And on top of the operating system or controller, we have a so-called northbound API, which has the role of enabling development of applications in top of the controller, which can be done either by the customer, by the vendor, or third-party providers. The advantages that SDN is trying to give is to offer this flexibility on moving resources along the network, of implementing new features in real time, and it comes with quite some drawbacks in terms of complexity, because all this configuration that it's now very mature, and all these protocols are moved and defined in software. So OpenFlow, it's now implemented into the current nodes, current switches. So the current nodes, they have the forwarding plane on the bottom. On top of this is the logic, the control plane, where we will have included a so-called OpenFlow agent, which will talk using OpenFlow protocol to the OpenFlow controller, and this will enable the node to have some of the ports running on OpenFlow and some keep working in the classical way, so have this hybrid behavior of the switch. Now, looking specifically at what OpenFlow is doing, this communication between the switch and the controller. On one side, the switch is able to send to the controller topology changes, statistics, and notification at every packet arrival. And from the other side, the controller is installing rules in the so-called flow table that it's creating in a node, carry statistics, or even send packets. But as we said earlier, every node will have a so-called OpenFlow agent, and under this, it's one or more flow tables that are defined as specified on top of the controller by the rules that are coming from the controller. So all the traffic that comes now into the node, it's seen not as layer 2, layer 3, or so on, but as flows. And these flows can be defined as a pattern of the traffic by choosing specific masks or patterns for layer 2, layer 3. And depending on the way we define a rule, we can make the switch to behave like the node to behave like a switch if we only choose layer 2 options, or like a router for layer 3, or like a firewall or a load balancer, or so on. This example, all the packets that come to the node with this IP destination that are forwarded to port 2. OpenFlow started in 2008 to be developed by Stanford University, and then it was taken by ONF consortium, and the specifications continued to be developed the first one, and with the one that is most present in the equipment now, it's OpenFlow 1.0. The initial target for this was campus research, and the main thing that is characteristic to 1.0 is the fact that all the packets that come to the node, they are matched, and an action can be performed on that. While afterwards, when 1.1 was defined, the action idea was developed, and it could contain a set of actions or even change the pipeline of the processing. And then 1.2 came and added support for IPv6 and multiple controllers, and the last specification of OpenFlow adds a lot of support on QoS and based on the meter table definition. So the vendors review the purpose of the work performed here. I tried to get in touch and analyze the offerings and the way the vendors see SDN from the three different points of view: the hardware, the controllers, and the application to be built on top, and where they focus on this, and afterwards how OpenFlow is implemented, in what equipment, what versions, and whether this is implemented as a firmware, a software update, or with dedicated chips. And a random order of them. First is Sienna. They announced the support of OpenFlow 1 month ago, like many of the others. Their OpenFlow implementation is in pre-production phase. As we also heard yesterday, their focus is on openness at both APIs. So on Soundbound API, they are running OpenFlow, and the reason for this openness at both APIs is that Sienna is providing mainly the hardware, so they want to be compatible with as many controllers or application providers. This month, they announced for the first time the SDN strategy aligned to the open vision. And in this SDN strategy, it's a different mentioning first of the hardware, where they offer OpenFlow 1.0 enabled in their 5400 switch series, and they are running OpenFlow in hybrid mode, so they can keep running the node with the classical way of doing it with control plane, or specifically with the controller. OpenFlow can run on 10G and 1G cards, and there are plans to run it on 100G and 400G in the future. Also for the next year, the service aggregation switches are planned to support OpenFlow 1.0. And from the controller point of view, Sienna is not looking into developing controllers, and they were doing tests in the Plugfest under ONF, and one of the main switches, as I could hear about, is big switch controllers that they tested. Then on Juniper, they announced their SDN strategy earlier this year. Their focus is on data center approach, because they are yet not sure on how this OpenFlow will go in the future. So implementing it in data center solution, it's more relaxed, and you can counteract possible wrong outcomings. And they focus on northbound API while they lower the importance of the OpenFlow. And the reason for this is that both Juniper and Cisco, they don't see, how to say, they don't see very well the way the OpenFlow is driven and taking the intelligence from the upper layers to the transport network or to the physical layer. They are rather interested in having as much intelligence from the physical layer on top and having their application more aware of what's happening in the network. However, Juno's SDK includes OpenFlow Client 1.0, and they enabled OpenFlow on the MX and EX equipment series. Juniper, there are rumors that they have to decide soon on whether they will start working on their own SDN controller or if they will choose another one. Also, the tests they've been performing so far were with the big switch controller. And in the future, their plan is to have 1.3, the latest OpenFlow specification, on the same equipment next year. Cisco, with a similar approach to Juniper, they give a lot of importance to SDN, but not to OpenFlow, and they launched the session1 platform, where they try to offer all these SDN features, low programmability. They have the session1 platform kit, giving APIs so the developer can create application on top of all the Cisco operating systems. They announced quite some time ago, more than a year ago, a proof of concept of OpenFlow 1.0 on their Catalyst switches, but since then there was nothing new about it. However, their plan is to enable this OpenFlow in Catalyst just for research and academia testing, so not on commercial purpose. So as a general view for Cisco, OpenFlow is just an enabler of the SDN, and when they have to talk about SDN, they try to emphasize less the OpenFlow. And their approach on future for OpenFlow, they describe it as being a wait and see attitude. So they don't commit on running OpenFlow, but they don't skip it either. So they just follow the market trend. Brocade, they introduced OpenFlow support in June in 2010, and they look for SDN solutions for WAN and service provider networks. The initial OpenFlow support was on their MLX router, and they enabled OpenFlow 1.0 in their latest operating system, 5.4, and all the equipment from Brocade that has older operating system, if they update it to 5.4, they're able to provide hybrid OpenFlow support 1.0, so the same switch running in a classical mode with specific ports in OpenFlow. And the novel thing in Brocade is that so far they are the only ones supporting 100G cards for OpenFlow. And also they claim that they have dedicated ASICs, and they are able to run OpenFlow at full line rate compared to many other providers that are only doing the firmware upgrade of OpenFlow, and they cannot commit to the full line rate for this. And late news from this month is that Brocade acquired a company called Viata that have a lot of expertise in SDN, so they seem to push further not only in the hardware with their SDN strategy. Big Switch, which might be not so familiar name on a list of vendors, I introduced it because it's the main controller that all these hardware manufacturers are using to show a full SDN solution. Big Switch is a startup created with former researchers from Stanford and engineers for the big vendors, and it's now the main startup in SDN market after Nicira was acquired by VMware. So there is a lot of focus now in Big Switch, and they are developing their own open source version of OpenFlow controller based on Floodlight. And the plan now is to provide this controller to as many customers, so they will it will spend some time in the market while it gets familiar, tested, and after it's mature enough, they will start providing applications and developing applications similar to Nicira on top of their dedicated to their own controller. Then IBM and HP, they both announced SDN strategies not a long time ago, last month, and they are looking, IBM is looking in all SDN layers, so they want to provide by themselves a full SDN solution, so both hardware, controller and applications on top. They are of course looking into data center mainly. They developed their PNC controller, which is OpenFlow 1.0 compliant. It allows up to 300,000 flows, and compared to the wide market of OpenFlow controllers, it's easy to see that their controller is not cheap enough. So it's interesting how they will manage to sell the whole solution. For the hardware, they have the top of the rack switch G8264, which is the same 1.0 compliant, running on 10G and 40G cards. However, for their solutions, as I could see, they're missing a core switch in order to do complete networking solution in SDN, and they use Brocade and Juniper partnership equipment. HP, on the other side, they started long time ago in collaboration with Stanford, development of OpenFlow and testing. They announced the SDN strategy last month as well. They are also trying to cover all the SDN layers. They developed as well a proprietary controller with support of OpenFlow 1.0 as well. Their controller is available either as a software or with dedicated hardware appliance. And they are also developing open APIs on top of the controller in order to enable third-party developers to create applications on top of this. HP provides probably the widest range of switches that are OpenFlow enabled in the market. At the moment they have 25 switches offered. I will not go in technical details of the switches. And they also have some commercial applications for the SDN where they try to provide virtualization, distributed load balancing, and security. NEC may be one of the most involved vendors in SDN. They have a so-called programmable flow family of products that altogether provide an SDN solution. One is the NEC programmable flow controller with a lot of features, virtual networking, custom filtering, and so on. They have two switches, 5240 and 5820, that are both OpenFlow 1.0 enabled, and also they have something interesting called management console, which allowed them to manage and to visualize the end-to-end connection, virtual tenant network, and so on. The future plans in NEC are to continue on the northbound applications and have the solution more attractive from the application point of view. Arista Networks, it's a young company that they try to exploit the merchant silicon market opportunities. They are focusing on data center switching as well as low delay networks. They have OpenFlow Agent 1.0 enabling their switches 7050 and 7150 on 40G and 10G and 1G cards. However, even though Arista talks a lot about SDN, they don't see OpenFlow as something mandatory in the SDN solution, and they would rather look for providing some proprietary ways for SDN inside their EOS operating system and based on FPGA switches, as well as trying to counteract this with network overlay technologies, VXLAN, and so on. They are doing collaborations with Big Switch, VMware, and Nebula controllers, so they try to show interconnection with as many controllers as possible for their switches. Another unusual presence in the vendor list for me, at least in the beginning, was Pika 8, a very small company, a startup founded in 2009 that is trying to do business out of OpenSwitch and the router platforms. The same, they exploit the merchant silicon opportunities, but compared to Arista, they are trying to stay open also in the operating system. They provide 3 small switches that are OpenFlow 1.0 enabled, 3290, 95, and 3920 on 1G, 10G, and 40G cards. All these vendors, they are doing a lot of interoperability testing under ONF consortium in the so-called PlugFest events, but they are also doing some commercial collaboration. So Juniper was trying to have a commercial solution with Big Switch. The first they demonstrated it at ONS in 2011, and actually the first commercial solution in SDN, OpenFlow based, that was also sold, was between IBM and NEC. They tried to offer architecture shown here with NEC's edge switches on top, IBM's top of the rack switches, and all controlled with the programmable flow controller from NEC. And they offer this to two companies called Tervera and Celerity. Tervera is a data fabric provider, and they were very happy because this solution with OpenFlow and SDN was able to provide them some predictable performance on big data that they couldn't achieve before, while on Celerity, that are very focused in ultra low latency networks, they were able to accelerate real-time decision making for the global financial customers. So these are two interesting cases where OpenFlow and SDN were able to provide to the network something new and not to reinvent the thing or just do it in another way, which is often the case. Also another example where OpenFlow is a success, it's Google, most probably everyone knows, and they were able to, again, to get a novel thing out of this and to run their network at a load up to 80% in the intranet. So again, there are use cases where OpenFlow can actually give something novel and not try to do the same things in a different way that they are today. And on the other side, there are cases where OpenFlow doesn't really seem to get in, like SDN. For instance, Telefonica, they were saying that even though OpenFlow and SDN will get mature in 3 to 5 years or so, they don't see themselves to move to SDN and don't see having a specialized software team in Telefonica and trying to do to get the knowledge of all this stuff. So they see all the SDN and OpenFlow thingy as redoing the things in another way, but without novel ideas. Then ONF, it's the organization that non-profit organization that is driving the development of OpenFlow. It was founded by 6 major providers and a couple of other software suppliers, vendors, and service providers. It drives the development of OpenFlow specifications. It's quite a closed environment. It requires a fee to be part of it. But the gains out of being a member is to get real-time participation in the evolution of the OpenFlow specifications, interoperability testing, be part of those Plugfest where the results of the interoperability testing usually don't get out. And they also offer the collaborations with the startups and people involved in driving OpenFlow development. And for more information, they have a website. So, concluding, SDN is a new trend that it makes aware all the entities that are involved in developing, deploying, or running networks, and it tries to bring a quite long list of advantages. I only mentioned the virtualization, the reduced operating expenditure because of having centralized control plane, and flexibility, but on the other hand, it brings a lot of complexity in the software side and a lot of other problems arising out of this related to security and error handling and so on. So OpenFlow is an enabler of the whole SDN solution. The specifications are driven by ONF. Big vendors started changing roadmaps, as we saw just the last few months, with regards to OpenFlow and SDN development. There are new businesses coming out on these new market niches like Nicira, Big Switch, or Pika 8, and OpenFlow 1.0, it's, I think, the only and the main supported version in the actual commercial equipment. There are high expectations from OpenFlow development in the future, and probably the technology could get mature for being commercialized by the vendors in about 3 to 5 years, as most people expect. So that's it. Yes.
So first of all, that was an excellent summary. I think it's a very confusing situation at the moment. That was a very, very useful presentation. This proprietary link that Arista, you mentioned for Arista, they're not using OpenFlow itself. Yep. Are they unique in that? Are there other people looking at proprietary?
No, they are trying to provide the similar benefits that SDN is giving, flexibility and some network virtualizations, but in other ways other than using this open API. So they try on specific use cases to use specific solutions like VXLAN or I don't know what other network overlay technologies. And I couldn't get more information on what's inside their operating system. So they talk a lot of having specific SDN characteristics in Arista EOS. Yes?
Yeah, you want very good presentations about all the flavors there and what they're doing. Have you been in contact with the Ophelia or the project that is called Ophelia that was also involved at some point in OpenFlow? I know that.
Yes, there are in the JRI1 where we are working. There are also the people that drive Ophelia, the people from UK in Bristol and in Spain. So yeah, they have a lot of hands-on experience on implementing OpenFlow.
Okay, any more questions for Jonas? No? Thank you. Yeah, for
Thank you.
Okay, so now if you remember from the agenda, we have the user case discussion. So I'm gonna hand over. So now it's time for exam. So maybe you can hand over some this way. Okay, yes. So actually, yes, is the idea with this user case is an excuse to get some good discussions ongoing. So everybody has a copy of the user case. So what we're gonna do now is actually we're gonna split all the people in different groups. You're gonna be working together in groups of 5 to 6 people. So 3 groups will stay here in this room. 2 groups will go to another meeting room in the other side of the building. And the idea is that you read the user case and you have to work with the user case. You will get some flip charts and some post-its to write down. So again, the main purpose of this user case is to get some discussions and write all your ideas, your challenges, your questions, and put it in paper. And then each group will have to choose a speaker that they later on will have to present what they were talking about. And maybe if you come up with a solution for the user case, that will be perfect. And we'll have to present it here when we're back from the discussion. So I think I have here the groups. We tried to mix the groups, so there was a mix of different profiles, and let's say group 1 will stay here, and it's Hobart. Sorry, because the names sometimes are Kasabuli. You stay also in group 1. Simon. Okay. Lars Lange and Felix. Felix. Yes. So group 1. So group 2 will be Marcin, Lidl, you are group 2. Rona, you are group 2. Yeah. Kamisa, you, group 2 as well. Tony Bridge, group 2. So if some of you are not in any group, please tell me so we assign you afterwards. So group 3 will be myself, Victor Oliver, Roderick, yes, Roderick there, and Kaufman, and Jeff. You will be group 3. So these 3 groups will stay in this meeting room. Group 4, Rasmus, you go to the other meeting room. Peter, Tony Gray, you will go to Henrik, Wouter, group 4, and Kuros. And the last group will be Thomas, you, Johan, Guy, you will be in group 5, Jan Radil, group 5, and Roland Nuit, group 5, okay? So, yeah. If you have any question with regards to the use case, just ask me. And we have like 45 minutes. And sorry? Yeah. So, is everybody assigned to groups, or is no? Who's missing? You stay here. If you stay here, you have to be part of the spectrum. Okay. Yeah. Somebody, you profile your oxygen.
Michael, did you fill out this?
Where did we go?
And there is some
Lars, du er gruppe 1, ikke? Du er gruppe 1, ikke?
Det kan være. Jeg skal bare være her.
Jeg er gruppe 2, hvor lige sidder derovre.
Ja.